Good afternoon, everybody. I am Dr. Preeti Scholar at IIT. Today, I will be presenting a work and of course, that contribution on behalf of my team. The outline of the presentation is as follows. Start with a quick introduction, moving on to current state of art, objectives, study area set, proposed methodology, and such. Flood detection is obviously a very crucial application which requires timely response. We need to mitigate the damage, we need to calculate the damage that's going on for resources such as saving life and general purpose resources as well. The most obvious and traditional way is classifying the data using optical as well as SAR imagery. As we all know, SAR imagery is a virtual radar technology. It offers the ability to gather Earth's data under different weather conditions. There's a flowchart that we prepared so that better understanding of the topic will be developed. Flood monitoring, as I said, could be done either by optical data or by SAR data or by physical data. If we use a modality optical data, we can implement traditional supervised and unsupervised learning classification of models. Then we can move on to machine learning and deep learning models. The only disadvantage would be that the cloudy season does not have the data availability in optical. So we move to SAR. In SAR, we have two categories, full polarization and dual polarization data. Same, we can apply the classification techniques and the machine learning techniques, but in full polarization data, they are not frequently available. Whereas in dual polarization data, there is limited information again. Using both the modalities, the optical as well as the microwave data can give us some benefit of doubt, where we can start with unsupervised, supervised, and machine learning-based models to detect flood detection. The pros is that we get a multi-sensor data model. Still, the cloud cover is a problem in research. So we'll move on that there's still a challenge to identify flood affected regions. The motivation behind this research is that flood detection, as I told you, is crucial for timely response, and Sentinel-1 data is freely available with temporal resolution. It can be a potential data source. We can also further use it with optical data of the same data in area. And use of machine learning algorithms in conjunction with SAR offers a diverse classification result. On the basis of this motivation, we formulated the problem statement, which is to identify the flood affected regions using harmonic analysis with an edge of machine learning approach on Sentinel-1. The study region and satellite data for the temporal study region. We have taken data sets over Dehradun and Hebbar in the state of Uttarakhand. The latitude and longitude are mentioned in the images. And we have taken two subsets to have a detailed analysis. Sentinel-1 C-band, DHBB polarization, 10 meter spatial resolution, well-based temporal resolution, 2020 to 22 data sets. So we split the proposed methodology into three parts. First, we presenting of Sentinel-1 data. We downloaded the product, check the calibration spectral filter, and then to terrain correction to the subset and collection of sigma band image for harmonic analysis. And we did different harmonics, average of sigma band, first harmonic, second harmonic, and we moved on to FCC implementation for the harmonic. So multi-temporal data analysis over large flooded area and partially submerged vegetation regions shown in the figures. For region 1, which is on the upper left, you can see the sigma dB, sigma pH. And for region 2, you can see the sigma dB, sigma pH. The observation is that from the temporal observation of the both pH and dB band, it is observed that both the pH and dB have a lot of potential to show the change in with respect to the flood to the water bodies, but pH is providing more information. So we move to the second part, which is the Fourier analysis and the harmonic generation using time series data. Over here, we talked a little bit about Fourier analysis, the ability to express the annual changes of the time series data with respect to flood monitoring. So it gets converted into cosine values as seen in equation 1, 2, and 3. And the Fourier coefficients are derived, and the Fourier series is applied for mapping the data using time series method. Now we'll move on to how it is actually applied. For that, I would like to share an observation of the first harmonics, second harmonics, third, and the additive term shown at A, B, C, and D of the figure. The first three harmonic and the additive term are calculated using equations and mentioned. And from the observation, we can see that permanent water stream shown in the red circle is identified in each harmonic as well as in the additive term. And in contrast, the transient water streams marked with the blue circle can be identified in both third and additive terms. Final is the FCC image generation. Then we go on to the machine learning aspect of the application. Over here, the region 1 in image A, the time series of present Page time series of 2021, and C is the reference color map. So region 1 is indicated with dark black color indicates both static value, glass, which is a permanent water body. Region 2 and 4, indicated with the dark color. In this color, additive term or the average value of the harmonics was given. And the additive term is dominating in light of the region covered with vegetation or the classes. Whereas the region 3 shows, shown by the red color, depicts the first harmonic, which also indicated the unimotive behavior. So we may consider the class present in this region in the flooded region, changes parts of the video. Coming to my favorite part, which is the XGBoost model. Now that whenever we have any kind of features for a machine learning algorithm, we can feed those features and train the algorithm to get whatever we want. So over here, we've used XGBoost model. The history of XGBoost model goes back to the simplest classifier known as decision tree. So you have a threshold and you make a decision tree. Then you have random forest classifier. Then you're bagging and boosting. And the cumulative machine learning aspect is the XGBoost. It's an iterative process. Why is XGBoost beneficial? The author I'm presenting this paper for did the primary part, whereas I'm a little bit responsible in the contribution over here. So once they took out the first, second, third, and the additive terms, we use that as a feature to train on the data set on the classifier. So we started with decision tree, which did not give us the classification. Then we moved on to random forest, which is also a form of kind of a decision-based learning in which different decision trees were combined together. And then we finally settled for XGBoost. Even in XGBoost, there were certain hyperparameters like the learning rate, maximum depth of the trees, the minimum child rate, and the gamma function. So these were the range of parameters that were the optimal parameters that gave us the desired result in this specific application. We can define the parameters as learning rate. Obviously, higher learning rate makes a model learn faster about the features. Maximum depth, the depth of the single most readed in the maximum is out. Minimum child rate, the number of samples in the inputs, and gamma is the lower bound. On the basis of the reference map mentioned over here, the blue color is the permanent water of the river, cyan is the submerged region, and we could finally resolve the pictures as follows. This is the classified map obtained with the developed model. And we have the reference map which we can refer to. That's the mask with the reference. So figure C shows a submerged mask obtained with the developed model. It's quite close to the reference map, hence it provides the potential of the developed model. The reason it's not colored right now is because we also went for another decision tree function so that we could clearly see why it does and also see if the model is overfitting or underfitting. I would also like to add over here that we use the cross validation metric, like the grid cross validation. So we had 5 training sets. We gave one after one each as training and the remaining as testing. Then we gave the second one as training and the other as testing. So that's called a cross validation method. We use the grid search cross validation for the same to get this desired result over there. So the conclusion for this overall presentation is that Fourier analysis definitely has a good potential with respect to the feature that we be feeding to the classifier to monitor the flood by using the SRAL data. And different seasonal annual changes in different classes has been from other harmonic analysis. We could also add a point that in further work, other machine learning classifiers could be used to deploy this problem statement, including maybe give a better result so we can go for the neural networks or CNNs. But this was a decision-based classifier that. Thank you for the references. They're not flash floods, they are over some time. They're like this is a basin area which tends to get flooded. It's about the intensity, how much it gets flooded with respect to time. That yes, they're the perfect river, and the flooding variation differs with time. Yes, we had good amount of temporal data. Right. Actually, the person who at the time we also worked is not present over here. I worked on the extreme most part, but according to my knowledge, we use the Sentinel-1 data and we make the reference map by overlaying it on Google Earth or via the satellite data. According to my best interest. Yes. The primary author has already completed his PhD and he has moved up to researcher. So he actually used a specific extreme algorithm on different blood regions, but the applications will not change. As we're saying that for takes for different water bodies, yes, of different sizes and dimensions we have used. We also they were researching the Hebbar district over the Naga river. There was a little bit of flooding, so we did during that time with the same extreme that's being used in a lab. Or are you asking the cross like the final parameters? So for the cross, when we started with decision trees and not the pattern calls. So whenever we were inputting the features of harmonics as well as it's not mentioned over here, but it should happen. We were also using all the separate band values as the features in the field. Now, when we had the, like, let's say we have one to n images and everyone has their own individual feature, so we randomly group them. We had random function and we randomly group them into one to n. Out of those, some were selected for training, the others were for testing. Iteration one, that's the K value, which is again not mentioned, but it's mentioned in the paper. So the K value kept on changing, like let's say K is 5. So we had 5 iterations, one, 5 of the training data set revolving in the classic one. This is for the yeah. The post classification metrics are not, but I am sure the mention of the should have been there. I got this presentation way last minute. It's not an experience, but I feel the cross validation I can tell you it was the reference map was used for cross validation. Something else. So we use the if you're asking about the modalities of the post classification methods, confusion matrix we use it we created a confusion matrix and on basis of that the accuracy is to be sure and the reference and the can actually target one. It's basically the usually the matrix of stress so the mask over the see that's the manual mask which is in the snap or NP products that gives a certain value and this is the classified dimension. So we compare the classified with the mask dimension, which is generated from the It's very nervous. I hope my original presentation, which is tomorrow, is not this. Thank you. For any questions, I would be happy to leave the email ID of the primary author if anyone is actually interested in questions. Thank you for connecting from here. Thank you. Once again, recently was successful Bangalore. Will present my research that on inspection techniques for the system of loss and storage, reservoir storage capacity, a case study which we carried out for Tungabhadra Reservoir. So these are my co-authors, Poompavai and Ramachandra. Reservoirs are essential constituents of any terrestrial ecosystem, and basically reservoirs are constructed for storage of water, which we can use when required. Mainly reservoir water, which is stored, are mainly used for drinking water, then hydroelectricity power generation. Then it also helps us to control the floods in the upstream and control the drought in the downstream. So reservoir elevation capacity is very important for planning and operation of the reservoir. Basically, this elevation capacity curve gives us an idea of water split area at any given water level elevation and the storage capacity of the reservoir. Basically, topographic survey and hydrographic survey forms the basis of this elevation area capacity curve, which will be generated for the construction of the reservoir to see the intended capacity of the reservoir. So these periodic surveys of the reservoirs are very essential to evaluate the change in the storage volume so that appropriate actions can be taken to store more water and for desedimentation, which can facilitate the optimal utilization of the water available. So the main input of survey data technology for our study was the water split area. Water split area can be easily mapped because of you can see a distance signature of the water in the optical data because it absorbs almost all the radiation in the NIR region. So when we display the MCC, you can see a distinct signature between the water and the land, the water boundary and the land surface. And in SAR data, it acts as a specular reflector, again giving us an opportunity or enabling us to map the water body accurately. Since in these reservoirs, there is a drawdown cycle and a refill cycle. Basically, refill cycle starts from June till October when the monsoon onsets and map the water split area very accurately. It becomes essential to have the monsoon data also. Since optical data has some limitations in the cloud cover region, because of cloud cover, they have used conjunctively SAR data from Sentinel 1 and optical data from Sentinel 2 for our study. So actually, background of the study is that Karnataka Engineering Research Station, which is situated in Mysore, approached us for providing the full reservoir level water split area, which we usually call it as an FRL contour for few reservoirs, namely Krishnarajasagara, Hemavati, Harangi, Kadiri reservoirs. Initially, these FRL contours or studies was carried out using only history data. So usually they specify the date when the reservoir is at full reservoir level, and we collect the satellite data to obtain this reservoir level water split area or contour. Recently, they approached us for providing these FRL contour for Bhadra reservoir and Yadav reservoir. As you can see here, that this is the polarization or these FRL contours were used to carry out the bathymetric survey by the KRS officials. Objective with this background, we took a case study for Tungabhadra Reservoir to generate an updated elevation area capacity curve and to see the feasibility of the study so that it can be extended for other reservoirs in the state. Also, recently, because of heavy rains, we are seeing that the reservoirs are getting filled up to the brim, and still there is some availability of less water in the summer season. So basically, the official quality study where there are sedimentation or where there can be positive sedimentation, so that they can take necessary steps for the reservoir planning operations. So these are my objectives. Generation of surface of the reservoir for 2019 to 2020. Then generate the updated elevation area capacity curve. Then computation of loss of storage capacity at full reservoir level and at reservoir elevation levels with reference to the base area capacity curves. These base area capacity curves are only part the area capacity was generated with the pre-impoundment survey of the reservoir when the reservoir was built. So this is my study area. Basically, Tungabhadra Village in Western Ghats flows down and meets at Kukunuri near Shivamogga, 13 kilometers from Shivamogga to form Tungabhadra River. This key dam or Tungabhadra Dam has been constructed at Malappuram village near Hospete, 5 kilometers from Hospete town, with an integrated capacity around 132 TFC, then with an catchment area of around 28,000 square kilometers. Multi-purpose dam where has water supply, then 126 megawatt of electricity generated with hydroelectric power stations. Then it is also used for irrigations down for 6 districts surrounded which are not wrong. Satellite data which we use for the study, basically computer data is similar to this temporal data. This study in fact uses the fact that the water step area decreases with the decrease in the capacity. So we have taken temporal satellite data from 13 December 2019 till October 2020. So for all these dates, we have water levels, the corresponding water levels from the KERS department. So this is my methodology. The SAR data, which we use for calibrated, then gamma maps was used was generated and unsupervised passes from the after correcting the data and classified classified the water uses. When temporal water spread maps were generated, this temporal water spread maps, that is water spread contours, we have attached the in-situ water levels which we have got from the KERS, and we have generated a 3D water surface for the reservoir. And then the volume was computed, and then the elimination in the capacity was generated, and the loss of storage capacity was computed. So these are the water spread vectors that of the data from the reservoir. As water spread data is stored, and once it comes to summer season, that SAR was made with the monsoon season, where the reservoir levels actually drastically changed. We need to map the water spread data and October data. You can see that the reservoir level was October and 8th October. Water spread contours generated from optical and SAR data were merged, and the reservoir level was added as an RF to the GIS domain. So this converted this whole thing to the irregular network to generate an elimination model for the reservoir. Basically, this volume also can be computed using the trapezoidal formula. So the study we have computed from the GIS domain as well as using the trapezoidal formula. So it doesn't, it was like for similar results. So we have used the GIS domain. Then, as you can see, this is my elevation level for the particular date of satellite pass, the water spread area created, the cumulative capacity computed. So on bus tour, it is showing that it has the least water spread that is around 5.67 kilometers square with an capacity around 151 million liters. And 8th October, it attained the 497.74. This is the FRL level of the reservoir with a capacity of 357.9 million liters with a water spread of 366 kilometers square. So this is the updated area capacity curve. So here, it's just to show that this elevation, that is on 22nd January, how the capacity area is made based on the elevation. So for 10th July, then for 14th October. This is my final. This is my final results for these elevations. Actually, we got these values of elevation from the KRS officials. With this, for this elevation, we have come from the area capacity we have generated. We have computed the area, then the pre-impounded, that is 1953. Then the satellite data in this area that have computed. Then the loss of storage capacity was computed for the reservoir. So at the full reservoir capacity level, the 366.18 kilometer square, the loss of capacity is around 651 million. So, my conclusions are this conjective use of optical and SAR data can be used for deriving water spec areas and calculation of the cumulative storage capacity. The updated elevation area capacity curve can be generated. Then the loss of storage capacity can be computed, which was observed in our case, 651 billion. So basically, it provides faster and cost-effective methods for generating water spread areas and the updated elevation capacity curve for any reservoir. So the future work will be validation of this accuracy assessment with mathematical data and extending this methodology for major reservoirs in the state to see the activity. How to be validated. So actually, we are in discussion with our NRSC partners, area division. They have a bathymetric radar. So we also have to see the feasibility. This will be our next work, which we will be taken up. Uh, no, it should be done when the reservoir is full. So yeah, after October or November, we can take up the subject. No, sir. We have done both this formula as well as the GIS domain. There was no major differences. Little only. Basically, whatever and whatever I'm saying with this study, that is a water spread area. So basically, these water spread areas will be converted into 3D contours with the GIS domain. So once you attach the reservoir level field as an RL database, so it automatically will convert these into contours and then the depth that it. Validation can vary mainly of the loss of storage capacities. Basically, we cannot validate each data set separately. So our validation will be for the final result. Very accurate. Yeah, it is very tough. Sir. Yeah, thank you. Yeah, charging stations I think is day by day, and the water level can only be monitored with the charging stations other than satellite. So with the use of satellite data, we can put the well monitoring of the studies data. As we know, reservoirs are much dynamic bodies where the water level will be changing drastically and which can affect everything. These studies will give us a scope to monitor them in a better. So coming to satellite argument, argument goes to the principle of measuring range between the satellite and the water level. So as we can see in the picture, ultimately basically there will be two important parameters, altitude and range. Where altitude is the distance between satellite to bottom of the water body, and range is the distance between satellite to the top of the water level. So this range is affected by ionosphere and troposphere. So this range is affected by ionosphere and troposphere. While coming to the as ultimately, as we know, it's especially designed for ocean studies. When we are applying it to inland water bodies, it's majorly affected by many other parameters, like it's a heterogeneous environment where vegetation comes into picture, build-up area comes into picture. So all these parameters we have to apply some corrections. Out of which I'm concentrating on wet tropospheric correction, which is the atmospheric moisture present in the plant. And the altimetry is really sensitive to this atmospheric moisture. And it's always a negative value made with wet tropospheric units. So my study area is Srisailam reservoirs. Why I have taken only minor tracks is there were already ample of studies covering the major tracks of reservoir where there are more footprints where you can get the data, ample data. But there are also pure tracks which you can see and where it will be covering a few prints. A reservoir like Srisailam, in India, we can get a water level data from Center Water Commission of India, where they will produce weekly water reports. In which, when I observed over the few reservoirs, the change between various water. While coming to Srisailam reservoir, it's almost more than 10 in a week, like from peak report to other. So this is my major concentration of the study, but around 69.75. And she said that reservoir is located on the mountain of Ahalya and Telangana, shared by the states. After the data used, I have the sentinel artifact data, which is a cave and artifacts with a spatial resolution as and this data is for a correlation and for comparison and the set of water level data, and also I have compared the completions of based Jyothi database. Jyothi is nothing but a database, a hydrological time series developed by and Institute of Germany, which has its based on a satellite data. They have a time series of water strength, time series of water levels. So my methodology is like covering the basic formula of water level coming to altitude, figures from range and with respect to MS. So by calculating this, I have divided it into two equations where first I will be calculating altitude minus range and ionosphere because these are captured by KU1. So there are two bands, KU and C1. Some parameters are captured by KU and some are captured by C. So there were dry tropospheric correction, wet tropospheric correction, which are called path changes caused by the troposphere of the atmosphere. So while calculating this analysis, I can say that I observed a missing of wet tropospheric data. Not just this analysis, I have made this conclusion after applying it to other reservoirs, which I didn't mention in this paper. But because of missing that one value, we are losing data on that particular day. Because of which we were hardly getting the monthly one water level per year. using this study, I can say that whatever the data is available, we don't need to miss the data on that date. We can just extract it by substituting that wet tropospheric correction by calculating it individually. So to process altimetry data, I have used a BRAD software developed by European Space Agency and QGIS platform to process. So while conducting this individual analysis of wet tropospheric correction, I have taken, so when I'm calculating, let's say 12 days of data in a year, out of which I can retrieve for 8 or 9 days wet tropospheric corrections. So depending on that, I have taken an average of wet tropospheric correction, and also I have compared it with the basic Sentinel-3 manuals where everything is mentioned, like how it is going to vary. By tallying it, I have calculated it over this reservoirs. It's typically varying within 50 centimeters, which is negative value. And I have calculated it average of minus 0.5, which I'll be showing you. So another estimation was done with the final water levels. So here with this, after calculating this individual analysis, the final water level is calculated with respect to MSL. So coming to the results and discussions part, these are the individual analysis of wet tropospheric correction values. These are the retrieved values based on which I calculated the value as minus 0.5 meters based on this 5 years. And it's constant for all the 5 years. As we can see, the variation is mostly from minus 0.47 meters to minus 0.52 meters, like all this. You can see almost every year I can retrieve 25 to 30 values, minimum of 25, and almost 40 values based on which I made the conclusions. So these are the graphs plotted between Sentinel-3A water levels and CWC water levels of 20 to 21, and we can see the variation, the proximity of calculated water levels. We can observe the maximum water spread is in the month of August, because this Srisailam area, it's mostly the monsoon season is from mid of June to September. So the variation we can see in all the graphs. This is the graph of 2019 and 2020. So we can see, other than the existing values, existing analysis, this study I could be able to calculate at least 12 values of the year, other than like major values, and which are also in a good correlation with the water level values. So as I have central water level values of weekly reports, I have calculated a mid value by interpolating the dates to calculate it with my data. So coming to this, as we can see from the previous studies, there will be always a constant error while applying this satellite altimetry over inland water bodies, that is especially a smaller water bodies. So in this case, I have observed a constant error of 2 meters over all the days. And as I mentioned it before, this reservoir has a heavy variation within 7 days, which is almost 10 to 15 meters per week. And maximum water levels were observed mostly in the month of August, and least will be from March to May, as it is a drought season. So error was estimated based on CWC reports, which is a correlation error of 0.98 and RMSE of 0.57. So I can mention the RMSE is not up to the mark, because as I mentioned, this is not the major track, and the minor track, it's hardly having 1 or 2 footprints where I got most of the error. But this study mainly focused on retrieving more water levels. So I can mention that than calculating 1 or 2, 1 water level a month, using this study, maybe we can measure all the data which were available. We can retrieve the water level of that days. So my conclusions will be the wet troposphere was measured as minus 0.5 meters, and seasonal changes were calculated, which can be drawn from the water level graphs. And the correlation error was calculated as 0.98, and the number of water levels measured for the year is almost double.
So this data I have compared with Dahiti data. Dahiti has done the analysis of the major reservoirs of India as well, in which Srisailam is one of it. And I have got the results, more number of and precise results than Dahiti data. So this data, so when we consider it as a future work, we can apply it for flood mapping, bathymetry studies, reservoir operations, and numerous other fields. So these are my references. It's like if we apply satellite data to, let's say I have done the same analysis for other servers, where I have observed a constant level of 1 point. So it's like it's designed for ocean studies. So they are they are getting that constant level which has to be mentioned. This has to be. Different of business cycles and not yeah, I have mentioned that also. Agree was bit more in some cases, but we can at least determine the values where we can't go. There were many reservoirs in India where others have values. And if we are using only Sentinel 3A data or something, we are hardly getting maybe hardly 10 values over a year. So if we can mention measure all these small tracks and if all these parameters measure it and do it manually, we can get more number of results.
So, good afternoon, everyone. I am Konik Deshakar. I am from National Institute of Technology, Durgapur. And today I am going to present on the article that has been selected for research track on InGARSS 2023 entitled Mitigating CH4 Emission from Hydroelectric Reservoirs Using Google Earth Engine and GRS, a study from a tropical reservoir. There are my other co-authors who have helped me on this thorough work. So, as of introduction, we all know that hydropower reservoirs are defined as the reservoirs built with the intention of producing energy. And by building a dam, we actually stores a significant amount of water and as a potential energy. And eventually, we pass this water into the dam base to generate electricity from it. So here are the three types of reservoirs. So impoundment reservoir, diversion reservoir, and pump storage reservoir. So we will be talking about impoundment reservoir as of this study. So we know that the world energy demand is ever increasing due to demographic expansion, economic development, and the urbanization. So here are the countries which are actually the world leaders of generating hydropower energy: China, Brazil, USA, Canada, Russia, and India. India possesses a hydropower installed capacity of 51,785 megawatt, and which leads to a total generation by hydropower of 174.5 terawatt hours as of 22 reports. So hydropower reservoirs, while generating clean energy, can disrupt ecosystem services, alter river flows, and the recent studies are showing that it is a significant emitter of greenhouse gases. So GHG concentrations are intensifying their catastrophic consequences on our Mother Earth by climate extremities, rainfall pattern changes, sea level increment, water quality, so on. So this is the importance of methane mitigation. By mitigating methane, we can actually mitigate climate change, we can improve air quality, and we can protect our ecosystem services and so on. So when we are actually building a dam, so we are actually impounding the existing vegetations over here. These vegetations got sedimented in the benthic zone, and when the anoxic conditions arise, then CH4 is being generated from over here. So as of now, 4 emission pathways has been detected. One is CH4 bubbling, CO2 and CH4 diffusive, and CH4 degassing pathways. So my motivation of the study. So I have fetched 470 articles from Scopus database using the syntax hydropower and GHG emission. It is showing the year-wise publication trend is increasing, and I have specially mapped these distributed papers in the world. So it is showing that more than 40 papers have been published by China and Brazil itself, and the whole world scenario is like this. So after the Kyoto Protocol of 1997, during COP26 summit of UNFCCC that was held on Glasgow, United Kingdom, so several developed nations like Britain, Canada, United States, and Japan were aiming to achieve net zero emissions by 2050. India has pledged to attain this target by 2070 itself. So we all know that methane is a great potent high greenhouse gas with a higher, like 34x more global warming potential than carbon dioxide. And in India, there has been not any comprehensive work till now to address these greenhouse gas emissions from the large hydropower reservoirs. So interestingly, with the previous syntax, when we are adding the Earth observation in our syntax, the significant amount of 470 documents only has been reduced to 18 only. So this indicating the newness and huge research gap in this field. So this leads to my research question, like how GHG emission, so Maithon is my study area, so I will discuss it later. So how the GHG emission from Maithon reservoir can be quantified using the Earth observations data, and what are the influencing factors related to reservoir operation that we can actually change to mitigate, help in mitigation of this GHG emission from that Maithon reservoir itself. So this leads to my objectives, like to quantify GHG emission from Maithon reservoir using Earth observation database, and to study the different influencing factors that are related to reservoir operation to mitigate GHG emission from the Maithon reservoir. So this is my overall work process, how I have done the work. So I have developed primarily two Google Earth Engine code. One is to fetch the CWC water level data, and with this, accordance with this CWC water level data from the GE database, we are going to fetch the water extent data to study the dynamic nature of the reservoir. And there is another Google Earth Engine code that will be fetching the important GE-derived parameters that we will need in the GREST tool to quantify the GHG emissions. And we have chiefs data for rainfall analysis, and this all data will be stored in the system storage, and we will go for the further analysis to found any parameters that are relating to the GHG operational that reservoir operation that we can actually further study to mitigate GHG emission from the reservoir. So these are the Google Earth Engine databases. We can actually primarily divide these Google Earth Engine derived parameters into 4 quarters. So one is catchment data, one is reservoir data, one is climate data, and buffer data. So if we can see, these are the parameters related to catchment that will be needed in the GREST tool itself to fetch the GHG emission from the reservoir. And these are the respective databases of Google Earth Engine from where we have actually derived these parameters. So just like this, these are the reservoir parameters that we'll be needing, and these are the respective databases from where we have fetched this data. So as of like it, so climate datasets and the respective databases, and that is also for the buffer data itself. So our study area is Maithon Reservoir. It is actually situated in the Jharkhand district, and it is under the Damodar Valley Corporation. So we have chosen this Maithon Reservoir as of like the primary objective was for this study was to estimate the GHG emission from the hydroelectric reservoir. So Maithon is a hydroelectric reservoir. It is not of the area of conflict, like we are choosing the database from one climatic zones at a time. It should not lie between the 2 climatic zones. So Maithon is lying between, Maithon is light tropical hydroelectric reservoir. And we are choosing a large reservoir that can help us in the remote sensing techniques to measure its water extent, as this water extent and water level values are dynamic in nature and can actually manipulate the GHG emission from the reservoirs. And So we have chosen this Mython Reservoir as of our case study. At first, we have done the rainfall data analysis of the Mython Reservoir. So this is actually showing us a descending zonation over the Mython Paraka River Basin. And we can actually see, interestingly, for the monsoon months, like from June to September, uh, when the rainfall, you can see when the rainfall, average rainfall is increasing, the water level is being lowered to maintain the reservoir in operating conditions. So this box plot is also showing the same trend. We will discuss this later when we will combine this with our GHG emission. So this is the basic workflow for our water extent measurement. So we have a GE code. Now we have CWC given water level data. We are choosing the CWC as it is a open domain and actually provides regular data and reliable source. So CWC is giving us data on particular dates, and we are actually defining our AOI, that is for this case study is Mython Reservoir, and a date range according to this CWC report. And if we run this code, then it will generate the water extent values for us. And these water extent values will be saved in the Excel format, and will be prepared this Excel-based database, and the GOT files we are going to get from the Google Earth Engine itself. So this will actually help us in studying the water level and water extent relation of the Mython reservoir. So here you can see actually temporal variation of the Mython reservoirs over the 2023, 22-23 water year from June 22 to May 23. And it is actually giving us a second degree polynomial and with a R square value of 0.96 and RMSE value of 2.54. So after that, we have developed the methodology like this. We have fetching the Sentinel-1 data, CWC water level data to map the water extent, and water level and water extent data are being analyzed for their relation. Then Chiefs data is being used for rainfall analysis that I have shown you. Then the next objective is for us to derive the required parameters to be used in the GRES. So GHG emission, so GRES will be actually estimate our GHG emission. Then we will combine this data and we can actually further analysis how we are going to work from here. So GHG estimation from the reservoir. So as of now, some physical quantifying techniques for GHG emission that are available right now are floating chambers, eddy convariance, infrared gas analyzer, bubbling trap, ultra portable GHG analyzers, etc. But integrating this Google Earth Engine derived parameter into reservoir water level with GRES can provide us an edge in terms of feasibility and data producibility. GRES is basically developed by International Hydropower Association in collaboration with UNESCO to actually quantify the emissions from hydroelectric reservoirs that we are talking about. So here is the second Google Earth Engine code that we have actually developed to fetch the required data that is going to be used in the GRES interface to calculate the GHG emission from them. So if we run, then you can see that reservoir data, catchment data. So it is going to be like this, and this overall data is going to be fetched into this GRES tool. That is actually will be like this: landscape, reservoir. We have to provide each data for this GRES tool, and in turn, this GRES tool is going to calculate and give us these GHG estimations. So the four parameters we are talking about, the pathways. So GRES is basically giving us this pathway basis GHG emission estimation. So for CH4 diffusive, CH4 bubbling, CH4 degassing, and CO2 diffusive emission. So next, we are actually we'll be talking about some mitigation techniques. So how we can actually mitigate this GHG emission that is happening from the reservoirs. So one technique is changing operating level. As we know that operating level and water extent area is a vital parameter and dynamic in nature. So we will be discussing about this. We can actually add a secondary intake over this thermocline. So under this thermocline, there is a CH4 reached water level. And if we can actually just shift our this intake just over this thermocline. So the CH4 rich water we can actually omit, and we can get more CO2 or oxidized water. So CH4 emission will be less. And this is another workflow. So if aeration has been done, so the water can be aerated and CH4 can be mitigated. And this is actually some Nam Thuyen 2 reservoir from Laos. They are actually applying this technique to get rid of CH4 that is being generated from the reservoir. And this is another technique. So methane has a fuel value, so we can actually store and capture this methane by some spray analyzer or some membrane technology that Brazil is now using. So you are going to find this from this Kuwait et al. 2019 paper and Ramos et al. 2009 paper, more about this. So in our case study, we are going to develop, we are going to actually check about the operating level, how it is actually changing our emission. So as of now, so we have actually from the dead level of the reservoir to the FRL of the reservoir. So we have changed 10 centimeter and we have done analysis this GRS tool for each 10 centimeter, and we have actually calculated how much GHG emission is happening. So interestingly, we have found that for increase in 10 centimeter of depth, it is actually reducing 2.01 plus minus 0.51% of CH4 degassing emission from the turbine itself. So 30 centimeter increment in the reservoir depth can actually decrease in 5.87 plus minus 1.43% of CH4 degassing emission. So as a conclusion, we can say that as of our answer of question number 1, the present study showed that the cloud-based tools like Google Earth Engine and GRS integrating with Earth observation data can be actually useful for estimating CH4 emissions. And as of our answer to the question number 2, we can say that this case study of Methane Reservoir showed the 30 centimeter increment in operating level. That is a actually parameter that we can actually manipulate, reduce the CH4 degassing emissions by 5.87 plus minus 1.43%. So as we are talking about in the monsoon months when the water was decreased, so if we can maintain a water level height like 30 centimeter or so, so we could have decreased this amount of CH4 degassing emissions from Methane Reservoir at that time. So this present study may help to strengthen our current hydropower policy to accomplish the sustainable development goals that we are looking for. So these are the references, and I am highly thankful to PVC for providing the water level data, and Department of Art and Environmental Studies and Civil Engineering of IIT Durgapur, IEEE and InGARSS 2023 for giving me an opportunity, and CGIA and Mitigate Plus for to support this research. So thank you. Actually, in Scopus, we have a search from where we actually search. If we are providing the keywords that we are looking for, then it can fetch actually the data, the articles that Scopus has indexed. So at first we have just hydropower and greenhouse gas emission. We have put the keywords. So it was fetching 470 articles out of it. But when we are just adding Earth observation data, remote sensing, or Google Earth Engine, like these keywords, so it is actually reducing to 18 only. So this can actually show you the huge research gap in the Earth observation data. Yes, ma'am, it was only for my motivation of this study. No, yes, yes, yes. No, yes, sir. In GRACE, what they have done, they have actually studied 223 reservoirs around the world from the different climatic zones. And they have developed empirical formulas for each parameters. Like, yes, for different climatic zones itself. Because you can see the trees for the different climatic zones are not same. Yeah. So, sir, GRACE is claiming that 223 reservoirs from different climatic zones of the world, they have actually made the empirical formulas for each parameters. So when we are actually giving the parameters over there in GRACE, so sir, you can see this is all already validated by UNESCO and International Hydropower Association. They are working with this reservoir and they have some papers which are showing the physical quantifications are almost lying with the GRACE tool. So 223 reservoirs, sir. Yes, they have studied this. No, sir, I have that India is lacking this GHG estimation. So, sir, yes, I was. So, sir, one thing I can actually say you that they have not studied for the reservoir dynamic nature, like for the water level fluctuations and water extent fluctuations, they have not measured the GHG emission. So I have done this on my study. For each 10 centimeter increment, I have studied for the water extent itself. And then I have provided these two parameters in the GRACE tool to check which water level and water extent is actually sir, changing the course of the GHG estimation, sir, that we are doing from the GRES tool, sir. Yes, sir. Yes, sir. Yes, sir. Okay, sir. So, yes, sir. Yes, sir. I do understand, sir. Yes, sir. This one, sir. So, sir, what happens actually due to thermocline, this stratification, so water is not allowed to mix with the bottom CH4. So, what we can actually do, we are taking intake for the turbine from this CH4 rich area. So, CH4 degassing is happening. So, if we can actually alter this intake over this, like if it is thermocline, so if we actually can manipulate our water intake depth, like if we are fetching water from over here, so it can actually mitigate that much amount of CH4 emission to be liberated into the atmosphere. More. Any more? So I am providing the email over here. So if you have genuine doubts, sir, so you can contact me later. Thank you, sir.
Hello. Yeah, good afternoon, everyone. My name is Sharnendu Shekhar Ghosh. Currently, I'm a PhD scholar at Microwave Remote Sensing Lab, CSR IIT Bombay. Today I'm going to talk about Sentinel-2 based vegetation health index, which was proposed by my colleague, Sandeep Kumar. So, to begin with, to understand health of a vegetation, we need to understand the kind of stress it experiences. Yeah, hello. So I will keep it like this, okay? So to understand vegetation health, we need to understand the different kind of stress the plant experiences. So basically, we can categorize the stress into two parts. So one is the biotic stress, another is the abiotic stress. So biotic stress is generally caused by the pathogens, the insects, or the herbivores. On the other hand, the abiotic stress is generally caused by water, the stress like because of heat. So, like when we try to understand the effect of this stress, we can say that because of this stress, the plant growth might be affected. And also what can happen is that it can affect so much that that the plant may also die after some time. So now the thing is that although this stress might be occurring at a cellular or molecular level, but the effect on of this stress can be observed in the on the plant when we see it over a more extensive range of like a spatial temporal range. So but what we can do is like that we can utilize the remote sensing systems to understand this kind of stress which is occurring over the plants. So and how we can do it is that we can utilize the remote sensing methods, and we can use to understand the various factors that might be affecting the plant health. So one of the example is the FFR, through which we can understand the photosynthesis rate. Now, the main elements of the plants which might be affecting the plant health are, we can the main we can point out is the chlorophyll content or the water content, right? So all these elements have their own characteristics, or we can say their own on methods or way of expressing themselves in different bands of electromagnetic spectrum. So when we think about the chlorophyll content, as we know that various indices have been proposed already in the literature, like the NDVI. So it mainly is dependent or can be related to the absorption by the chlorophyll in the red region. On the other hand, if we focus on the moisture index, it is mainly dependent on the absorption by the water content. So now what new or what extra do we need to understand water stress? So we need to consider actually many more factors or external factors that might be affecting water stress. And as far as we have understood, these proposed methods do lack in that aspect. So that's what our method is trying to cover. So, before going to the formulation, let's understand some theoretical basis. So we can see a strong absorption by chlorophyll in the red region, a strong reflectance in the near infrared. we can see a shift in the red edge when the plant changes or the from the healthy to the more of a stressed condition. And also we can see that there is strong absorption by leaf water in the range of 9.6 micrometer to 2.2 micrometer. And also we can see that there is absorption by the protein present in the plant leaves in the 2.2 micrometer. So this was the formulation proposed by Sandeep, and we can see that it has been proposed in terms of normalized difference to reduce the effect of the topography. The main bands which has been included are the already used NIR, red edge band, which is mainly present in the Sentinel-2, the shortwave infrared 1 and shortwave infrared 2. Now we will come to that why these bands have been used and what are the reason behind it. So we have validated utilizing some lab experience and some global analysis too. So coming to the lab experience part, so what it was done that, so there is Ashoka tree present in our campus. So we took leaves. So we took leaves in their healthy condition, stressed condition, and dead leaves. So we used the spectroscopy instrument and we took 5 spectras from different locations of the leaves, and it has been plotted over here. So what we can see over here is that we can see a shift in the red edge as the plant condition or the leaf condition moved from healthy towards the dead. So another few observations which we can see is that we have plotted over here the conditions of the leaves and according to their index values. Now, a valid question which might come up over here is why the value of the NDMI, the moisture index, and the proposed SVHI is less over here. So the reason is that because it was a lab-based experience and the spectroscopy was the sensor of the spectroscopy instrument was very close to the leaf. It was around only 4 centimeter. So what happens is that in a real life scenario, when the SWIR band is reflected or is transmitted, so there is absorption in the by the atmospheric water vapor. So that is absent in a lab setup. So you can see a reduced values. So another point to be noted over here is that if you can see there is a decreasing trend in case of NDVI and SVHI in terms of when we are moving from a healthy leaf towards the dead leaf. So this is because this the effect of the condition of the leaf has been that could be captured because the stress condition has been majorly influenced or majorly influenced in the red region or the red edge region. But because this visible region is not being utilized by NDMI, so this trend is not visible in case of NDMI. So what we can conclude from this is we cannot use NDMI to understand any kind of stress that is occurring because of the chlorophyll content. So next, in another lab experiment, what we did is that we took 15 different leaves and they were all in healthy condition. And then what we did is that we took similar spectroscopy measurements and we also measured the volumetric water content in all of them. So this is so again, the 5 spectras were measured and it has been plotted over here. So these are the different volumetric water content over here. So what we can see over here is if we see the initial water stress condition. Okay, so one more thing I forgot to mention is that, so these experiments were performed, these spectroscopy measurements were performed for 4 days. And in those 4 days, these measurements were taken. And after that, for the next consecutive 7 days, we kept it on the top of our department terrace and we let them dry completely until their weight was changing. Okay, so these were the changes. These were the different water contents. So what we can see over here is this change in the water content was more prevalent, and the trend could be seen in case of NDMI, which actually depends on the change in the water content and the proposed index. But the initial water stress was not observed in case of NDVI. So in case of NDVI, what we observed was that the change was only very dynamic, only when there was a very high water stress condition in the leaves. So next, we performed a check of the SWIR1 and 2 bands that we were using. So we checked the sensitivity of these 2 bands, the change in their reflectance with respect to the change in the water percentage leaf water content. So we saw a very high correlation, which justifies the utilization of these 2 bands in the proposed index. So next, after the lab experiment, we performed a global sensitivity analysis. So we considered over here 2 physics-based reflectance models, Prospect 4 and Prospect 5. And we checked the sensitivity of NDVI, NDMI, and the proposed SVHI model with respect to the equivalent water thickness and chlorophyll A plus B content. So what we observed was that NDVI and NDMI did not show much sensitivity or equivalent sensitivity towards the water thickness and the chlorophyll content, whereas the proposed central two-based vegetation health index showed this kind of sensitivity towards both of them. So in another validation, global analysis validation experiment, what we tried to show is that we try to understand that for different levels of chlorophyll A plus B content and water content, how for different other plant parameters and tree parameters, the particular proposed vegetation index is sensitive. Now, the idea was that we checked for the Prospect 5 model, combined the Prospect 5 model with the SAIL model, and also the Prospect 5 model along with the INFORM model. So the SAIL model is kind of a homogeneous leaf canopy model, and the INFORM model is kind of a heterogeneous leaf canopy model, or it is also called as the forest model. So coming to the application point of view, we try to utilize the proposed health index to check the phenology of corn crop over the Iowa region, USA. So these are the plots for both phenology maps utilizing NDMI, NDAY, and the proposed SVHI. So anyway, the phenology maps for all of them are pretty good. But if you look very clearly for the 14th August, so this is the case for the NDVI. So here you can see it was not able to distinguish much between the phenology of the crops, of the corn crops and the other vegetation. So just for the reference, so these are the corn crop areas and these are other vegetation, and there is a river also over here. And another problem, so what we can conclude from here is, although because NDVI is mostly related to the greenness because it is sensitive to the absorption by the chlorophyll. So what happened over here is it was not able to distinguish between the healthy vegetation and the corn crop present over here. Finally, another observation which was seen over here was the 16th September, which we have zoomed it over here. So this is one river which is present over here, small lake, not a river, I'm sorry. So NDMI was not able to distinguish between the water content over the, or the moisture over the healthy corn crops and the vegetation and the water body. So these are the various limitations of these indices that we have tried to understand by this application and by the previous lab experiments. So finally, we performed a temporal scatter plot between all these three indices, and we saw there was a high correlation in between them. So what we can conclude from there, it is that although the proposed indices are individually related to various plant elements like the chlorophyll content, the water content, but if we think about the differential sensitivity of both leaf water content and plant water content and other kind of stresses, then in that case, for a global health monitoring application, the proposed index can show promising results. So thank you so much. If you have any more technical questions, you can definitely, or I will try to answer. Thank you. Yeah, so that's a very good question, actually. So as far as I inquired with Sandeep, he performed it on Google Earth Engine. So yeah, so for validation for the global analysis, I think he's still working on that. Yeah, the lab one. Yeah, so in the case of lab experiment, as I showed. Yeah, so for validation, in the case of lab experiment, so the first lab experiment, we took three kind of leaves of the Ashoka tree, one in healthy condition, another stressed, and another was dead condition. Oh, so that I think Sandeep will be better because I only helped in picking up the leaves. So yeah, we looked at the live condition of the leaves and we analyzed. Yeah, yeah, thank you. No, no. Yeah. So that's what I think from the lab experiment, because we first validated, because as far as my knowledge, he started first with the Google Earth Engine application. And then because he was questioned by our professor that you need to validate it in the lab experiment, or else how can you justify the utilization of these bands? So that's when we conducted actually the lab experiments. Yeah. Yeah. Uh, I don't think I will be able to much answer about it because I don't know about the technicality of this. Thank you so much.